Hey folks, so welcome back to lesson 35A. This is sort of the second half of the order of magnitudes lesson, and it's really a different topic because we're now really going to get to the nitty-gritty of what is the standard model, and you to describe what it is and describe the particles and interactions of the standard model, although we'll focus on this a lot more in the next lesson as well. So first of all, here's a wee graphic of what the standard model looks. It involves something called forces, quarks, and leptons, and you're going to learn about what all of these things are over the next couple of lessons. So first of all, what is the standard model? Well, the standard model is a model or an idea of what matter is made up of and how it's all held together. It's got two main ideas. Number one is that all matter is made up of particles. So that old joke about why can't you trust atoms? Because they make up everything. I guess it's the same with the standard model. And secondly, this is the really strange idea, is that particles interact with each other by exchanging other particles associated with the fundamental forces. Now, there's a lot of physics packed into here, so we're going to try and tease that apart over the next couple of slides. And one example of this is the electromagnetic force, and this is something called a Feynman diagram. You won't be asked to kind of explain these, but I thought to include it just to show you what some of the standard model can involve. Okay, so standard model and field theory. So how does this compare? Well, if you think back to electric fields, there I said to you that the reason why positive and negative charges attract each other, or they can make things move at a distance, is because of this concept or model of an electric field. And for all intents and purposes, this works very well because we can talk about electric fields, we can do calculations with them, we can use them in a whole range of things like particle accelerators. We know gravitational fields work very well too, but there are limits to how well this model works. And whenever there's a problem with a model, scientists will then try to come up with solutions to that model. And quite often that means you have to alter your model or come up with a totally different one. So the standard model is a much more different interpretation of how particles interact. And so this is the typical standard model type of diagram. Okay, now mathematical equations describe the particles in the standard model, and in fact it's one of the most successful scientific models that we've come up so far. They've allowed experiments to be designed so that each of these particles can be detected and measured accurately. And so far, all of the particles that it predicts has been detected. The most recent one, of course, is the Higgs boson, and this is why there was so much buzz about it a couple of years ago. And Peter Higgs actually won a Nobel Prize, along with a few other people who predicted the existence of the Higgs boson. Now, even though it's a very well proven and very successful model, there are still some issues with it, which we'll look at in the next slide. So before we move on to look at the limitations of the standard model, here's a couple of famous scientists, and they're not the only ones, there are lots, who've done quite a lot of work towards the standard model. So Richard Feynman, as I've come to say to you already, he came up with the Feynman diagrams. He was also an incredibly clever scientist, and he was a gentleman that was put in charge of figuring out why the space shuttle exploded in its mid-flight. Peter Higgs, who was basically at Edinburgh University, and he came up with the Higgs boson. This lady here, Fabiola Gianotti, I think that's pronounced that correctly, is the Director General of CERN, or at least was at the time that I made this slide up. So, what are the problems of the standard model? Well, first of all, the standard model struggles to describe particles at high energies similar to those following the Big Bang. One of the reasons for this is because we've not really been able to replicate the same conditions, i.e. we've not been able to smash particles at high enough energy that were similar to those during the Big Bang. So we don't really have much information about what those particles might be, so we can't make any theories about it. Okay? It doesn't take into account the effect of gravity. which is one of the four fundamental forces of nature. And this is something called the hierarchy problem. And we'll look at these fundamental forces of nature a bit later on. It doesn't describe what dark matter may be, although again, this is more kind of current research and people are trying to use particle accelerators to see if they can make dark matter. It doesn't explain why the particles exists. Now, Feynman was very smart and he said that, if you ask a why question, you can always keep asking why. It's like a little 4-year-old that might say to you, why is the sky blue? You give an answer. Well, why is that the right answer? And so on and so forth. The better question to ask is, how does something work? Because if you say how something works, it means there's a process, there's a mechanism there which you can discover and figure out. So this slide here is really important because it gives you the whole picture of what you need to know for the standard model. So my top tip to you is if you're revising the standard model, make sure you can reproduce this diagram from memory. So remember, the standard model says that all matter is made from particles. And so these particles have two branches, fermions, which are called matter particles. And if you're wondering where this name came from, do you remember the scientist Enrico Fermi? Well, he did a lot of work on the standard model as well, so that's why we've named these particles after him. Bosons, which are the force-mediating particles, so these are the particles that are like messengers that allow particles to interact with each other. And if you think about it, Higgs boson, that's where this kind of comes from, or the other way around, I suppose. So example of these are photons, gluon, and Higgs. So we'll talk more about these a bit later on. Fermions can then further be divided into a group of particles called hadrons. And hadrons themselves consist of quarks, e.g. protons. And the other group of particles are called leptons, which do not consist of quarks, and these are called electrons, and there are other types as well. So try and remember this kind of tree here. Particles make up everything. They can be grouped into fermions and bosons. Bosons are particles that mediate the force between particles. Fermions are the matter particles. You then have hadrons and leptons, which make up the fermions. So this slide is a really nice slide. It shows you all the different kind of particles that make up the standard model, and you can see there's quite a lot of these. The quarks have the names up, down, charm, strange, top, and bottom. When physicists named these, they were a little bit whimsical, so that's why they've given them quite strange names. Leptons, the electron, which you know very well. Then you've got something called the neutrino, or the electron neutrino. You've then got muons, the neutrino muon, the tau, and the neutrino tau, or the tau neutrino. Your bosons, you've got your photon, gluon, your Z0, W minus, W plus, the Higgs, and the graviton. So all of these are particles in the standard model, and because there's so many of them, we usually call this a particle zoo. Okay, so here's a much sort of clearer diagram there, and you can see again the arrangements of these particles. These are the quarks, these are the leptons, which do not need quarks to make them. These are the mediating particles, and the Higgs stand outside them. These are the main particles that you need to know. There are lots more, but usually if you see them, you don't really need to understand what they are. They usually explain what it is, so don't panic if you see a name of a particle you've never seen before. As long as you know these ones, you'll be okay. And then you've seen this diagram before, but this is just another way to give you some of the information. And so you've got things like the mass. Remember, the mass is given in terms of electron volts. The charge, so these things have charges, and we'll talk about these in a bit more detail later on. Spin, we're not going to talk about at all because it gets quite complicated. And you can see they are grouped into 3 generations. And as you move along the generations, the mass of these gets heavier. Okay? And beyond the standard model, there is another model called supersymmetry, or SUSY. And the idea of this is that for each particle, there's a superpartner that's thought to be slightly different from it is like a mirror image of it. Okay, it's nothing to do with dark matter, but it is a theoretical idea. And the reason I've included this is because the names for these are quite cool. You add an S in front of it, so a quark would be called a squark, a lepton we call a slepton, and a Higgs is called a Higgsino. And because we don't know much about these, physicists think they might actually be the explanation for dark matter. The jury is still out. Okay, and one of the key things is none of these have been detected so far. So that's why it still remains a theory. Okay, finally, how small are the smallest constituents of matter? So you can see we've got atoms made up of a nucleus. A nucleus is made up of protons and neutrons, and we know that protons and neutrons are made out of quarks. Now we can't really see them, so how can we show they exist? Well, to show they exist, we know that they can interact with each other. We know that we can manipulate them using magnetic and electric fields, and therefore we can use them to change their kinetic energy into some other energy like light or heat. Okay, now going beyond the standard models, there are even theories called string theory or M theory, which suggests that quarks themselves may be made up of vibrating strings. I won't say any more because the topic gets really, really complicated. There are lots of really fantastic videos on YouTube if you want to search that to learn more about it.